in this section, we're going to finish out by looking at the idea of a tree. And a tree is going to be a connected graph with no circuits in it. All right. So basically, and remember, a circuit is basically saying you can begin and end on the same vertex, and sometimes you don't necessarily have to repeat edges. One of the rules about trees is that a tree with n vertices has n-1 edges. All right, so let's just go through and take a look at some of the basic elements of trees. And so we want to draw a tree with 5 vertices and 4 edges. This is really easy. All right, so 1, 2, 3, 4, 5. All right, that's a tree. It's not the only way to draw it. All right, there's lots of different isomorphic types of trees with 5 vertices, but that's one of them. Okay, so another one, if you chose to, could be like the cluster like this. So you could have one like that sort of thing. All right, that's another non-isomorphic type of tree to the first one we drew. All right, so a couple different ways. Right. For letter B, we want to try to draw a tree with 7 vertices and 7 edges. And unfortunately, that's not possible. All right, so if we have n equals 7 vertices, this implies that n-1 equals 6 edges. So we would say not possible. So that might be the first thing we do, is we even see if it's feasible to construct a tree. All right, by using this sort of simplistic parameter to start with. We have 11 vertices, 10 edges, so that'll definitely work. But now we have some other constraints. So total degree of 20 and 3 vertices having a degree of 3. All right, so at least by this rule, it'll work. But let's just see if it works by with these constraints. All right, so you might want to pause the video and see if you can do it for yourself. All right, this is the way that I would do it. All right, so I just started out with a singular vertex here and another one, and then I just kind of stemmed off of that, and another one here, stemmed off of this, and then here to here, and then I just had 4 more vertices in succession. All right, and just imagine these are filled in. It's not as easy on my screen to fill these in all the time. All right, and so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And if you were to count the number of edges in there, that would be 10 edges. And look, and these are the ones with degree 3. All right, so that would be 3 plus 3 plus 3. And then we have a 1 and a 1 and a 1 and a 1 and a 1. And then over here, we have 2, 2, 2. All right. And so if we add all these up, all right, so this is our 10 right here. And then we have 6, 7, 8, 9. So did I miss one somewhere? Let's see. What did I miss? So it looks like we have 3, 6, 9, 10. And we need a total degree of 20. So we have 1, 2, 3, 4, 5. And then we have degree 2, 2, 2. All right, so it looks like I might be missing a 1 somewhere. 1, 3, and 3, that's going to be 10. And then, oh, I forgot a 1 in here. Duh. And so that would give us our other 10. So that's degree 20. And it looks like that all of the different conditions are satisfied. Okay, so that does indeed work for us. I'll get rid of all this just because we don't need it anymore. All right, so now to finish this out, we have 2 other types of problems, being able to draw these non-isomorphic types of trees. All right, and essentially when we draw non-isomorphic trees, we just want to make sure that we have maybe one vertex of unique degree. All right, so we want to try to draw all non-isomorphic trees of 4 vertices. So one of them is just going to be our straight line. All right, another one could be like our cluster, similar to what we had up here. So we could have 1, 2, 3, 4. All right. Now notice these are non-isomorphic because this has a degree of 3 And notice that this graph does not have any vertices of degree 3 in it. All right. And I believe that those are the only two non-isomorphic trees that we can draw with 4 vertices. All right. So now, obviously, as we start to increase the degree of the tree, then we're going to have more possible non-isomorphic graphs or more non-isomorphic trees. Right. The last question we have asks, what is the total degree of a tree with n vertices? All right. So here's the way I would do that. Okay. So let's just start off with n vertices. Right. And let's just draw our tree. And let's have the degree. All right. So clearly, if n is equal to 0, then this is what our tree looks like, and the degree is 0. Okay. If n equals 1, then that's what we have, and the degree is still going to be 0. If n equals 2, then this is going to be our tree. All right. And the degree of this is going to be 2. All right, because we have a degree 1 and we have a degree 1. If we have 3, all right, then we're going to have 1, 1, 2, and that's going to be 4. And if we have degree 4, or n vertices, excuse me, then the degree is going to be 1, 2, 2, 1, 6. Right? And then if we have 5 vertices, all right, they're 1, 2, 2, 2, 1, and that's going to be 8. All right, and you can clearly see each time what are we doing? Well, we're just including another degree of 2 because we need to make sure it's connected. So this is 1, 2, 2, 2, 2, 1, 10. And so what's our formula that, or what's our closed form? It's basically a sequence, isn't it? And so if I come down here and I have n vertices, well, a way to think of this is that, okay, well, this is going to be 2 times 2. This is 2 times 1, 2 times 3, 2 times 4, 2 times 5, right? So there's going to be a 2 that seems to be static in the answer. And notice that right here, so this is 1, which is 1 less than 2. And this is degree of, or 3 vertices, and 2 is 1 less than 2. So a way that we could write this is 2 times n minus 1, where n has to be greater than or equal to 1. Okay, so, and obviously n is an integer for this case. All right, if it's not, then we'd start getting a negative number of vertices. All right, and that doesn't necessarily make sense. So if you're kind of faced with one of these types of problems with the total degree or something like that, you can always sort of put it in this fashion. And wouldn't it make sense that if we wanted to prove this, I just asked you to be able to find a formula, okay, for this, what is the total degree and y? The y would be that we just add 2 to the degree each time we add a vertex. All right. And this would be our answer. All right. But isn't it pretty obvious that if we wanted to try to prove this by mathematical induction, because remember, induction says it's valid for the nth case, now we can verify it for the n plus 1th case, or k equals n plus 1, or n equals k plus 1, however you define it, then to be able to prove this, at least using some sort of valid proof method, we would have to use mathematical induction. Okay, so that's it for trees, and that's all for graphs.